Hey everyone, welcome to another Haskell study group. I'm your host, Ram Vedam with Atlanta Functional Programming. For the last couple of weeks, we have been covering the concept of type classes, concept that's pretty fundamental to the Haskell type system. And we've covered how one might end up, leveraging a type class instance, how we might generate type class instances directly or via the deriving keyword. We provided examples where we had, a couple of trivial types that we used using the data constructor, and we ended up creating our own instances of the EQ type class, as well as implemented some fairly complicated type classes as well that allowed us to, leverage some of the built-in functionality for comparing things like days of the week. Today, I thought, we'd complete our discussion of type classes with kind of an example. This is something that was inspired by what was explained in the book. This is actually an example that's in the Haskell book, which we were using as supplementary material. And in Chapter 6, particularly Section 612 on type classes, that I thought we'd discuss here at length a little bit, just to understand some of the material. So I'm just writing out the reference here for folks who are watching Haskell book from. First principles, right? Chapter 6, section 612. Okay. In this particular example, although trivial, it is something that kind of gives you an idea on how one leverages type classes. It kind of illustrates the importance of having this type class interface. And we've gone through a lot of this with reviewing at a fair level of detail the type classes that are last week, like EQ, the numeric type class, num, ordering, enum, show, and read. But those are type classes that already have minimal implementations, so it might be interesting to note as to how one might end up writing a type class ourselves, and how does the dispatching mechanism. We'll be reviewing the dispatching mechanism today a little bit more to give you an idea as to, again, how when you write your algorithms or when you write your functions and you add constraints, what does that mean to the Haskell type system? A lot of this is somewhat a summary of what we've covered the last few weeks, but I think putting it all together really gives you an understanding of, okay, this is not only what's available from the built-in available type classes, but this is kind of the design pattern one might want to take in order to write our own. So, just a brief review again. What is type classes in terms of dispatching is necessary to go through this example. Okay, recall that a type class is more of a set of operations. Okay, they are a set of operations, and in many cases there might be values which are constant functions. That all instances of the type class must provide in order to become in order to be a valid instance of that type class. Okay, although this is somewhat precise and requires a little bit of understanding of what that means, it's important to make sure you pay attention to what it is. It's a set of operations and values that all instances must provide in order to adhere to that type class. This is very important because type class instances are a binding. It's a mapping, a unique pairing between the type class and a given concrete type. Okay, and it is what is necessary and what is used by the Haskell type system, especially after they've inferred the base types that are being passed in, the concrete types that are being passed in by to a particular operation. Those concrete types that they've inferred are what they use to actually figure out, well, what type classes does this particular type implement? Do these type classes instances exist? Okay, they exist. That means they have implementations for these operations. So let's go ahead and use those instances operations, and they do a quick lookup to go through that. Okay. To quickly specify this. So we said, like, again, type class is a set of functions and or values. Okay, this is straight up, to quote the book. This is an important thing to remember. The reason why this is important to remember is because a type class does not define a concrete instance of anything. All right, it is an interface that you leverage. It's kind of like an entity that you don't instantiate, like an abstract class. All right, you instantiate, you create instances that implement those operations. That's in a sense, implementing the type class interface for that particular concrete type. So you're registering those implementations yourself, all right? So there's a clear separation of concerns of the type classes and the actual instances that implement that type class. Okay. So one thing to note about this, again, is types that do not implement the type class. And although different type classes may have the same functions, that doesn't necessarily mean that it's the same type class. May not be, well, this is actually what will happen. They do not implement the type class if passed into a function that requires it. We'll throw that error of constructing the type. We'll throw a type class construction error, right? This is like the closest thing I can think of what exactly that error requires. But basically, it's that cannot construct or cannot look up an instance of this particular type for this type variable. Okay, and remember, our type variables are generic when we end up getting instituted into the actual no, 1 second. I just realized that I just got a question here regarding the. One second. So there's a question about the live Hangouts chat things. For folks who are interested in joining the chat, the Hangout chat, there is the Hangout link will be posted in the YouTube live chat for folks to keep track of. Just give me a second here. Okay. So, as I was saying, this is particularly important because what this is telling you is types that do not implement the actual type class ultimately will fail a lookup, and it's actually on you, on the designer or the implementer, the person who wrote those custom types, to actually go and write those instances out. Okay. And again, what those type class instances are providing is the actual implementations. How does that given concrete type use or implement those particular functions of the type class? How does it require those operations to be implemented or behaved within the context of that concrete type and the rules associated with that concrete type? Okay. So an example of that the book provided is a somewhat contrived and actually a very an example that several sources have said don't necessarily write conversions like this, although just because when you're writing a type class yourself for a particular new type class family or something like that, like for example numeric, you might end up providing something that allows one to, for example, in numeric you have this from integer function that allows us to take an integer and convert that into any instance of this particular type class. You could do somewhat the same thing. Let's say that we want to generalize this, all right, in the context of a number, and so we create this thing called numberish. All right, again, this is numberish, and again we have our type class A. And numberish will contain two functions, which I will first write. Remember, when you're writing a type class, you write the name of the type class, and you have to use a generic type variable, a lowercase letter, to actually go and determine what that type class is. It's typically a lowercase letter. It's bad style if you don't use anything otherwise. In this type class, we have two functions that we can essentially follow, much like this from integer function that we see here. All right, and we are we're taking an integer right now, and we're going to provide a number, and a to number we're going to use here, and we're going to go ahead and implement this. Okay, and let's say that we end up wanting to write a simple, type, okay, on ages, all right? So I'm going to show you one thing that we would normally do right now up in this point. We've written age integer data constructors and type constructors the following way here, deriving from PQ and show, using the data keyword. Okay, and remember this side here is the type constructor, and then the side on the left hand side is the type constructor, and the right hand side is the data constructor that will construct the rules associated with the data. Now, this will actually work. This will actually show you that you're registering a type here. All right. The one thing though is, and this is common for this particular case, notice that the type rules for creating this particular type, like age, has only one rule. You're going to take an age and you're going to take an integer. Okay. In that case, Haskell provides another keyword that you could use. Instead of using this, you could actually use the following, which is new type. Okay, this is another thing that basically because we have a single rule for construction, this is actually according to the Haskell wiki, the new type declaration is basically the same as the data constructor declaration using the data keyword, but and they could be used interchangeably only if we have a data constructor like this that we see here. Okay, let me just go ahead and delete this for a second here. If you have a data constructor like the following, and there's only one exact data constructor for this type constructor, okay, and more importantly, there's exactly one field for that type constructor, all right? Then and only then can you use new type to actually go and construct a new data type. It's a very restrictive version of doing type construction. We'll go through it later in more detail, but I just wanted to mention what exactly this is for. There's a huge slew of features related to actually leveraging this. Now, the book that we're covering, unfortunately, introduces this keyword without going into too much detail about it until later on. I feel that this was somewhat of a... This is why I'm actually bringing up some introduction to it, just so that you folks that are watching the stream can have an understanding of what this new keyword is, especially if you're following the book to understand what it is. But for now, you can think of these two as being equivalent, although new types with a single data constructor has some implications with the type system. Specifically, it deals with once compile time type checking happens, the rules of the type construction and the data construction, especially if you have a different data constructor than the type constructor, in this case where we don't, they will have no overhead in terms of being converted between the two. Because with more complex data types, you might have multiple type constructors. Multiple data constructors for a given type constructor. You will end up like having to do a little bit more at compile time to realize which type you're actually constructing, which concrete type you're constructing. An example of this is essentially our day of the week. Each of these, you could think of these as a single type constructor with no arguments, all right, that ends up requiring a little bit more overhead in terms of checking which type is actually being constructed, although they're all associated with the same type constructor. It's part of the type family. Does that make sense for folks? Okay, so once we have this data type here, this concrete type, we want to implement the type class. Now remember, we've actually covered implementing type classes multiple times in previous discussions. Basically, we're going to have to create an instance of the type, restricting the type on the age. Now remember, the difference between this is I'm using a generic type variable there, and here I am actually creating a new instance. Before I create the new instance, though, and complete the new instance, let me just comment this out for a second. Let me just load this to show you what we're dealing with in terms of implementing a new type class for ourselves, okay? When you do an info on numberish, you're going to see that we're only going to get the type class definition that we've already provided, and Haskell actually did a very clean thing for us in that it actually introduced the minimal implementation that you need to create and implement in order to actually adhere to this particular type class, okay? Ignoring where it's actually defined, okay? You don't necessarily need to know this unless you're debugging much larger scale programs and you have a lot of custom type classes. You can ignore this line for now. Once we have this, you could see immediately though that well, first, numberish is considered a type constraint. We have our type class, but we don't have anything registered to it. Okay, we have no instances of any concrete type. Well, that's because we haven't actually implemented anything at this point. So we're going to have to go in and actually create that. So to do this, again, we use the instance keyword. Remember, instance where we're going to have a constraint there to actually do this. And we just now go ahead and implement this. Well, there are two functions we need to implement. The first function, it takes an integer and returns our type variable, okay? So this now is integer to age. This is age to integer, okay? So let's implement each of these one at a time, okay? From integer to age, you're going to have to go there. For integer to age, you could just simply go ahead and construct the type, all right, for from integer, all right. Now to number, all right, which is taking taking our type, we have to first go ahead and specify what exactly we're constructing here. So on this side, we're actually going to have to do a type construction, all right, data construction. This is just a template for the type system to recognize that this is our a, or lowercase variable a. So it's just saying to number of some age number, all right? We're just going to go ahead and return that, okay? This is something that's pretty nice for folks who are coming in from other languages. You're essentially writing rules for the specific type construction, but the way you're doing it is you're on the left-hand side, you're essentially providing a template of how would you construct that using the data constructor, all right? Once we have this and we load this up, immediately you're going to see a difference in the type class instances. Just like before, we see the custom type instance that we've created, and now we have our type class instance implementation, okay? With this, we can now use this function, this type class in implementing various functions. For example, although we can, let me just go ahead and mention that this doesn't have to necessarily be implemented for just this type. You can implement it for other types too as well. The example in the book actually goes through and implements it for different types of custom types that we take in an integer. I can just quickly implement those too as well. So, for example, if you have year, that takes a year integer, and you're deriving, because we need it for showing, and we go ahead and implement our numberish on the year. Now, the reason why I'm there is some stuff to be aware of when you're doing this. Mainly is, and it's going to be shown later that there's going to be some weirdness here when we start using this. All right. Okay. Actually, I take that back. It won't be that weird because of the fact that we're going to constrain this on the generic type variable in this example. Okay. So we now have essentially two implementations of our numberish type class, okay? So what's the big deal? Why is this so useful, okay? What exactly is this going to allow us to do? Well, remember when we talked about generic algorithms and use of type class constraints in Haskell last week? And when you're implementing particular types of functions, what you'd want to do is first write the function in as generic a fashion as possible. So, for example, you might have something called some numberish, okay, that starts out with a generic type signature such as this, saying that we're just taking in, it's a curried function of 2 arguments. But by doing so, you're going to essentially have some issues, okay? Mainly in that this in and of itself is not going to help us, okay? Because we can't just do a plus a prime, okay, and suddenly we're going to get an issue. Well, that's because of the reason why we're getting this error, all right, when we compile and load is because we're using the plus operator. Remember, the plus operator is defined on numeric types. It doesn't know what type this type variable is or this type variable. So there's no way of actually inferring that these two are of the same type. And therefore, it just aborts compilation, aborts interpretation, kind of gives you this error message to talk about. Notice, though, when we talk about this construct, that it tells you what the fix is, okay? So add a numeric type here. But we don't need to actually do that. If we actually just call our numberish here, okay, in this example, which is what we're going to be doing, we'll see that this immediately will throw a different error. Mainly, it can't actually figure out the types of the numberish, all right? But remember, if it's a numberish interface, we've already implemented something that will convert our types instances, all right? The instance of the concrete type being passed in has an argument to an integer using the numberish interface, okay? As long as it's an age or a year and it adheres to the numberish interface, we have the toNumber function that we can actually call because we can then dispatch. Again, remember, we infer the concrete type, look up to see what instance of this concrete type, whether or not it exists for the type class. If it's there, we'll call that implementation for that particular function for that given concrete type. So here what we'll do is we can actually write the following, right? We could write, let's say that we will implement this. And there's a couple of ways of implementing this. One way of that is let integer of a equals toNumber of a. Actually, let me do this differently. Let me use the where clause, like it's in the book. We'll use, actually, let me take that back. Let me try this. This should work. Integer of a equals toNumber a. Integer of a prime equals toNumber prime. Sum equals integer of a plus integer of a prime in. I think we have to get the indentation right, otherwise it's going to throw an error. In, let's see here, from number sum. So what we're doing is we're converting it first to integers or to numbers, but they are really integers, and we're going to go ahead and convert it back to the type that we've specified. All right. So this compiles. So let's try it out. All right. If we do some numberish age 10, age 25, we get age 35. We're actually adding ages together. Same thing here, some numberish year 1920, year 1930. This is kind of, it's adding 1,930 years to the year 1920, and then we get the year 1930. Now, also, just to complete our discussion here, you cannot mix these together because, again, when we construct the instance of the SUMNumber-ish function, it recognizes it's left associative, so it's going to complain that age year is not an age. There's no conversion from year to age. Okay. So the expected type is age, and the actual type is year. So we can't actually mix those two together because once the function is bound, it's constructed with those types. It cannot be. It's not going to use the inferencing to actually go and determine what how to convert the other two. All those types have to bind to that particular concrete type. This matches the generic type variable that we see here in our type signature. All right, all of them have to be the same type. Okay. So when we look at the signature a little bit more deeply, right, a couple things will come out. Let's actually take the example of type 10. This is essentially what I was talking about earlier. This type signature here that we're end up seeing, because it takes the first argument and binds whatever its types to the type interface, and age is of numeric of numberish. Age implements the numberish type class. Everything ends up getting generated, and you end up having to have this type class interface constraint that says the type variable must be age, which means all values being passed into this function must be of that same type. Okay. But what if we don't provide enough information to an actual function that's part of a type class? Okay. So what I mean by that is if you have a function, let's say and it can be any function. Okay. This is numberish. In here, you can have say, and although this is again very bad practice to do, don't do this for defaults. Let's say that you wanted to create a function that creates a default, all right? And this is going to be a constant function, so whatever you pass in, you don't pass in anything, you're just going to return a value, okay? So one way of doing this is implementing it this way. Although this is, again, very bad practice. You can create a constant function that just returns something. And now you can see immediately in our editor, we're going to get warning that we have missing methods. So we're going to go ahead and implement the missing methods here. And we're going to say that we have age, let's say age 0, right? Saying that this person is just born, all right? And same thing with, let's go ahead and make this year 0. Okay, so we have a default for now for numberish and for age. All of this is now, registered. It's compiled, right? But when you try to run default number, okay, and you hit enter, you're going to end up getting the following. And that is oh, hold on, my apologies. I should not have used parentheses here. We don't need to use parentheses here. So the first thing that you will see, and this is again a little different for newer our what's it our REPL, in that you should actually get an ambiguous type variable error compared to what is in the prelude. So give me a second here. I'm going to actually load a shell just to see if my editor is causing some issue here. Shell. Okay. And go GHCI stack level. Let's see what this. Okay. And let's load PC example.hs. Okay. And if we do default number here, so for some reason it's getting eaten up by the Emacs editor for some reason. So this is what we should be expecting. So when you try running default number in the REPL, okay, what you're going to end up getting is this ambiguous type variable error, which is arising because when it returns, when the type variable returns something, it doesn't know which type it's actually dealing with. And as a result, it says, sorry, I'm trying to print something to the console, but the type show is returning a bunch of results when I query for a concrete implementation of the show method, okay? And it shows all the different types that implement the show method, all right, inside GHC show. So the way to fix this is simply by providing the actual type that we're actually dealing with. So if we actually go ahead and implement this here, we can actually see that we can get what we're expecting. Okay, but this should actually show you something about Haskell. One, if it can't infer the type, it's going to throw up an ambiguous type variable. If it has no idea that what instance of the number type class interface to dispatch on, it's going to give you the results of all the different instances that are available, and then it will tell you, hey, provide a type type annotation to restrict what type you're dealing with, and everything will work out fine. And this actually shows you what it's dispatching on. All right, you're essentially controlling the dispatch, the type dispatching, by explicitly providing the concrete type that you're actually going to be dealing with. Okay. So, as a brief aside, I'm going to just mention this again. Although this example that we covered is implemented like this, okay? Type classes in general should not be implemented in this way, and that's because of what type classes represent, okay? Type classes represent essentially a higher level description of a type family, okay? They are laws and rules and behaviors that all concrete versions of types that are implementing the type class must adhere to in order for it to be registered into the type system, and everything kind of works out, okay? In that sense, a class like numberish, right, is an arbitrary class that doesn't have any sort of real rules as to what makes it numberish, all right? And as a result, the functions that we've written here, although they can work out, you don't need to implement them this way using a type class. You could just simply use a function definition to actually go and implement that. So, for example, if you have you can actually implement a from number here that takes an integer and returns a type variable. Okay, and you could specify the rules on how you want to implement this for different types. Otherwise, and so for example, if you pass in and here you can even restrict what types you're actually dealing with. So like you could say they're all a part of the numeric type family or type constraints in order to deal with it. You just do not need to write a type class for this specific type of description. Okay, does that make sense for folks? Okay. So throughout our discussion of type classes, we've actually brought up our discussion of polymorphism, polymorphic functions inside Haskell. And you may recall that Haskell has both parametric polymorphism and constraint. Well, they call it constraint, but really it's ad hoc polymorphism in Haskell. The Haskell book calls it constraint polymorphism. All other books on the subject, this includes Learn You Haskell as well as other ones, call it ad hoc polymorphism. But the idea is we have two different types of polymorphic functions inside of Haskell, all dependent upon the type the type signatures that are provided for our functions. And one of the things to note about this discussion is the fact that when you are generically defining a function, and we kind of went through this earlier, you are essentially dealing with errors that are being thrown up, okay? And again, this error that we saw earlier, if we didn't define this, let's define another one. If we defined our good old add function that takes in two variables and returns something, and we don't specify anything about what the types are, we're going to end up getting an error because of the fact that our type class constraint does not exist in this signature here, okay? In fact, you can see that already because of the fact that there's it has no way of knowing what type it is, and it knows that plus is defined on anything of a numeric type, okay? So you have to go and fix this. But what if, so let's go ahead and do this, okay? If we do this, everything is good. We don't get an error. Let's go ahead and do something a little bit more, even more complex. Let's say that we do a non-negative add. All right. So basically, we're only going to add non-negative numbers. Okay. So we got this. We check our signature. We go ahead and we do a non-negative add with the same issue. Let's say that x is greater than 0 and y is greater than or equal to 0. Then we have x plus y, else it will just return the left-hand side, okay? Or we'll just return, yeah, it'll just return the left-hand side, saying that we got an error. Okay, it'll treat it like an additive function. Okay, we'll end up getting another error here, right? We'll end up getting more issues related to our algorithm and how our algorithm is structured. Okay, you know what, this would be a little bit better with add or return identity. We'll call this because we're essentially treating it as an identity operation. And we get this error because of the fact that we essentially do not have the ordering. Remember, the order type class is the one that actually implements all of our less than or greater than or our relational operators. All right. So what we need to do is our ordered operators. So what we need to do is we need to actually go ahead and specify in the type signature the actual types that are that need to be that need to adhere to that type class constraint. There's a question here as to the why. Why? Could you be more specific? Why what? Why we need to specify the type class? Okay, I'm assuming that the question is there's a question on why do we need to specify more of the type classes. Again, this is all related to how the algorithms are implemented, how the functions are implemented, okay, and how functions are getting dispatched on type inside of Haskell. You need to specify the type class for these generic functions in order for the type system to recognize what operations need to be present for a concrete type in order for that function to execute correctly. All right. In this case, we have a numeric type that numeric itself does not actually implement anything other than itself. So there's no type class constraints on numeric. You could think of this as a base level type class. So it doesn't actually inherit or get information about the ordered operation for a given type because it has no idea. So the way to fix this is first create a signature that allows us to additively add more constraints. And remember, the way we do this is we can create a tuple that says something must be ordered in numeric in order for everything to actually work out. And again, this can clearly compile and everything actually works out. So what happens is if you remember when we discussed this, this is an additive type constraint. This is checking to make sure that for a given type A, all right, A implements the ordering type class. Sorry, not the ordering, the ordered type class and the numeric type class. Okay, it has to have both in order for this function to even take in. Otherwise, we'll get a type error. Okay, but what if we wanted to actually only implement if we know we're only dealing with a given concrete type, all right? Well, we could certainly do that by just going ahead and explicitly calling it out. You know, we can actually say, hey, we're adding only integers, okay? We are only adding integers. Or we're only adding 2 integers and returning a different integer. So we could do it like a check equality thing between 2 integers. Might check, like for example, we might take 2 integers here, and we return a bool, and we'll say my check a prime. Call it equality check. Okay, a prime, and all this is doing is checking that these two are equal. Okay. you can see that this did not complain, whereas when we're dealing with generic type layer, it was complain. Well, that's because of the fact that we've provided concrete types. We've provided concrete types that implement particular type classes, okay? And since we provided a concrete type that the type system can look up, a given concrete, since a concrete type implements all the type, has all of its type classes already implemented in the type system, as far as the type system is concerned, by providing the concrete type, it automatically knows what instances of the type classes it needs to look up for those particular operations. It knows that since you provided an integer, we have the numeric implementation, the EQ implementation, order implementation. So it does not need you to provide any additional information related to the concrete type. You do not need to write, all this other stuff related to the type class information, because it already knows by seeing integer what type classes it's dealing with, and it can actually go look up seeing where the instances are and then give you even a more specific error than what you currently with. For example, if you're using an operation that a specific concrete type didn't actually implement, so it'll go ahead and deal with that. So there was a comment: type classes are used to specify functions that can be applied to objects. You're right. Type classes are that is correct. Type classes are used to specify functions, but they are behaviors that aren't tied to any specific object. It's a set of operations and a name that essentially creates an implicit type family that the Haskell type system leverages whenever it encounters a specific concrete type to see if that concrete type adheres to those operations in order for a function to get executed correctly. Right? I know that that's a huge slew of words to describe that type dispatching mechanism, but again, you just need to think of the type class as being nothing more than an interface for a set of behaviors that need to be implemented for a given concrete type in order for a function that requires that type class to get executed correctly. Okay, and to get executed at all, because if the type class instance doesn't exist, it means the behaviors don't exist. So Haskell has no way of actually knowing how to execute or even evaluate a particular function for this given concrete type. So it's going to go ahead and just throw an error. It's just going to say, look, I don't know what you want me to do, so I'm just going to hand it off back to you for you to handle how to actually deal with it. Okay. One of the differences and one of the reasons why this style of defining a function is encouraged over actually dealing with concrete type implementations, it has to deal with parametricity and what you're dealing with in your type class constraints. If you're dealing with writing, or you're attempting to preserve and create generic algorithms, all right, what you're actually wanting to do is you want to describe in your algorithm or in your function what operations you need to do to deal with your data values that are being passed into the function. Okay. By being explicit in terms of the behaviors at the top level, you can deal with more constraints or less constraints by just passing in the appropriate concrete type into the same generic function. As long as it implemented that type class, the behaviors, it's understood that the behaviors as implemented by the type class instances are at least preserving the rules on how to actually on how to actually deal with that particular concrete type. Okay, an example of this is actually what we're seeing right now with integer. Okay, um, int is a very big set. It's a countably infinite set. Okay, yes, technically speaking, it's machine representable, and yeah, you have this thing called overflow, and yeah, we know that there's ways to actually knowing when you're dealing with int max and so forth, and all these rules from other languages, and Haskell certainly preserves a lot of that. But if you think about it in terms of sets and or even objects with operations, you know that it's a big data type. It has a lot of members, right? So what can happen is you could unintentionally allow certain um, uh, values to come through into your function that you didn't necessarily want. So what the type class does is it will actually then take this uh, and allows you to be very explicit upon what operations need to be present, and it is on the responsibility of the type class instance to say, okay, for this constraint type, I have these more constraint rules that need to be followed in order for me to actually behave this particular way for this particular function. Okay, so these are essentially nothing more than laws and rules that you have to specify for your concrete type because it is type specific. Each type has its own ways of dealing with particular transformations, particular rules. So by having this top level interface provide the names, what values need to be valid inputs and what values need to be valid outputs, you are essentially telling using sorry for using this overloaded term, the interface for people who are implementing that interface, what your valid inputs and valid outputs are, and have them deal with making sure that it maintains correctness, has its mapping from this valid set of inputs into this valid set of outputs, and let the type system do what it's actually intended to do, which is figure out what type a given input is, figure out what constraints that concrete input type implements, okay, or check to see if that instance is available for use in a function, and then dispatch on that instance once it finds it, or throw an error if it doesn't. Okay, these four things for the type system in Haskell to work, you have to actually embrace type classes. You have to embrace these rules, so that way, while you may start out with writing functions with concrete types like we have here, with just because you're comfortable with it, as you move more towards writing generic functions and writing functions with more generic operations, adding those type classes, those class constraints will make your functions that much more reusable, and you're actually leveraging the type system the way it is intended in terms of dealing with maximum flexibility. Okay, so I'm going to take a small break here and open the floor to questions because we're almost done, and questions and comments. So one comment that we got was about, again, this is related to the running comment about type classes used to specify functions that can be applied to objects. There's a comment that says it's a set of constraints to specify for a set of types. One thing to note about type classes is you do not need the concrete types to be available. It is just for given type input being passed into a function. That concrete type needs to adhere to a set of type class constraints for that function to execute. Okay, a type class is nothing more than literally just a set of functions that instances must be implemented. They are the type class as a whole specifies a constraint that needs to be checked in order for a function to get executed. But an individual type class is nothing more than a set of functions, type signatures for what could be represented as a much larger set of types. Okay, and you can abstract that around that type class if that really helps you understand how type classes work. You could think of it like a family of types, if that would help. Does that make sense? Silence in the chat is assuming to be approval of the explanation. I'm just going to assume that other questions from our live chat, our live stream audience. Okay, so the last topic that we're going to be talking about, just very briefly, is type class inheritance. We mentioned type class inheritance in various forms in previous discussions on type classes. But I'm just going to be very brief on what exactly this on this subject. But one thing I wanted to point out, just merely for folks who are following along in either the book or may have Google open, wondering about all the different type classes that are in Haskell, is if you want to chart out the type classes in Haskell that are already available, you have these base level type classes, and those are type classes that deal with essentially what we had before, which is, for example, instances. Let me pull this up. You have this kind of structure here. Basically, you have a type class with a name and a type variable, but you don't have necessarily any additional constraints on the type variable in order for the type class to be even looked into. Okay. Recall when we talked about some of our type classes that are built in. Specifically, let's take, for example, let me just go ahead and move up my REPL here so we can get some more room. The ordered one, which is the simplest one that for checking for comparisons, okay, to compare different things. If you recall, the ordered itself has this class constraint saying that the type that we're ordering that type must provide some sense of equality in order for us to do any sort of comparisons. Okay, and again, this is very important if you recall, specifically for things like, say, less than or equal to or greater than or equal to, but it's for other things too as well. But this syntax here, okay, remember this class constraint syntax, and we've seen that with even the more complex one that we saw for our function signature. That can be used even in this case too as well. So remember this syntax here, where we're actually providing a more complex constraint, okay, an additive constraint. This can be used inside the signature here to specify the type class, class constraints that a particular type needs to adhere to in order to implement another version of this type class. Okay. The point is, this, when used in the declaration of a type class, okay, if you recall, it actually is specifying the inheritance structure of the type class. Okay, so this is mentioning, in a sense, it's an implicit inheritance. It's not like extends. If you're thinking of, oh, this is a subclass of this class in the object-oriented sense, that's the wrong way of thinking about it. That is not what this means. Okay, type class inheritance is nothing more than providing relationships, certain constraints that have to be satisfied in order for higher level constraints to be activated. All right. Think of it in terms of rules inside of like a rule-based engine. These facts must be true in order for this next thing to be true. All right. That's kind of the best way for me to kind of give you in terms of an analogy here. The reason why I'm saying this is oftentimes when new Haskellers, and I've actually have been encountering this myself when I'm looking at the literature of different books, we see inheritance, and for folks coming in from object-oriented programming especially, that has a very very explicit meaning, especially coming in from say Java and C++ and Haskell or Python or whatever that use OO. In this sense, inheritance is nothing more than additive constraints that need to be satisfied in order for the type class to actually go and be constructed. Okay, so these are preconditions in a sense. Okay. And they're only existence checks. So in order for the ordered type class to be able to be implemented, the EQ type class must be implemented. That's essentially what you should read this as. Okay, if you don't have EQ implemented, you cannot implement ordering. All right, and it goes on if you start adding complex constraints here. All right, inside your type class. The structure of this is very important too as well, in that the ordering on how you specify the rules. I think there's some rules related to how those are kind of adhered to, like in terms of complex constraints. I'm talking about specifically things like this. You may want something to be checked against as a numeric type before it's going to be checked against ordered. But I think it's a sequential check to make sure that these things are available before you can actually go and run it. I don't know if the type checker runs concurrently against each given type class for a given type. That is a complete unknown for me. This here. When you're dealing with especially complex type class constraints in terms of an inheritance structure, what you want to make sure that you're dealing with is essentially type classes that don't inherit from each other, right? Mainly because you're being redundant in the type signature in terms of what you want. Okay, most often than not, when you're implementing you could be very specific or you could be very generic, but if you're trying to be generic and specific at the same time, you're being redundant. Okay, What you want to do in a type class signature for an inheritance structure is essentially deal with base classes a lot. Yeah, you can actually have subclasses too for being more restrictive, but it's just be careful when and look up the type class inheritance already available for a given type class if you're trying to maybe specify as a class constraint for your type class to make sure essentially you're not repeating yourself in your class constraint constructions. Now, when you're reading in the Haskell literature, you're going to end up seeing a lot of folks talk about superclasses and subclasses. Okay, the one thing that I encourage you to do and I implore you to do is not think about superclasses and subclasses in the OO sense when you read some of this. All right, you want to actually go ahead and think about this in terms of constraints and constraints for a type. Right, the only purpose of the of these type classes when they're class constraints is what set of operations need to be implemented in order for this structure to be instantiated. Okay, that's all what this is saying. Okay, in order for us to implement this stuff, we must implement EQ and not EQ, or the minimal implementation for the EQ type class in order for it to be instantiated. Google and other resources on Haskell will give you somewhat of a hierarchy for some of the available type classes inside the Haskell type system. And these are the built-in ones that are especially in the prelude. I also suggest you take a look at I think in the Haskell wiki I saw some of the top level classes too. There are a couple of other resources that you could use at your disposal in terms of how to actually look up some of this information. Honestly, I would suggest looking at Google in terms of built-in type classes, just because that seems to be more up to date in terms of what's being available when releases come out. And of course, folks reading the book, there are a couple of papers by Wadler on dealing with type classes that you may want to read if you want to get more information on this. Folks out there, I suggest you, if you have a way of accessing Wadler's papers, like how to make ad hoc polymorphisms less ad hoc or type classes in Haskell, I encourage you to read some of those just to get some of the more theoretical foundations out of the way. I mean, you're not going to necessarily use it on a day-to-day basis, but it'll give you more of a deeper understanding than what we just covered here the last couple of weeks. Although I hope the last couple of weeks kind of gave you a good foundation on to be able to leverage what is available out in Haskell already. The one thing I will suggest, and this is kind of the final thing I would suggest to anybody, is as with anything, I even say this even with algorithms with any language that I'm dealing with, check the standard library, check Prelude, and other third-party libraries already available, okay, to see if there's already a type class available that you could just use as a class constraint to actually solve your algorithms, because you're improving the reusability and you're improving the you're actually making your APIs far more flexible instead of writing your own type classes. If one doesn't exist, go ahead and write your type class. The main reason I'm saying that is obviously we don't want redundant type classes that essentially have the same set of operations. Obviously, there are probably some ways of unifying some of that kind of stuff. It's just unnecessary overhead from the standpoint of a person starting to read a Haskell code base. If you're using a type class that's already available, you could just look it up in Google to actually go in and figure out what operations need to be present and what do we have or not. So that's the end of our type class journey. I appreciate you guys joining the last couple of weeks on our type classes stuff. Next time, we're going to be talking about functional. We're going back to the real nitty gritties of functional programming in Haskell, and we're going to be talking about things like higher order functions, point free style, and so forth next week. For those who are following the book, this means that we're going to be discussing functional patterns that are in Chapter 7 from the Haskell book. Those who are looking at Learn You a Haskell, I think what this is equivalent to, I've got to pull it up again just because I, for some reason, closed it. This is similar in, guys, as to Chapter 4, 5, and 6 inside Learn You a Haskell. Although there might be some updated information in the Haskell book that Learn You a Haskell doesn't cover. So when some of those things arise, I'll let you guys know. For folks who, as a final note, for folks who are reading Learn You a Haskell, a lot of the stuff that we've covered today has a review. If you really wanted to go through it, read both Chapter 3. Where was it? It was Chapter 3? Yeah, it was Chapter 3 and Chapter 8. That covers more or less the implementations. And in Chapter 8, you're essentially going through up to type synonyms, I think, if I remember correctly. And it's going to be the same information. Just letting you guys know, though, if you're reading Learn You a Haskell, algebraic data types introductions and stuff like that, we will be covering again later on in a different topic. That's much later on in the conversation. But some of the stuff that we talked about in terms of type class implementations, implementing your own types in type classes, are covered in that chapter, in Chapter 8. I'll let you guys know later on, though, if there are other materials that we can leverage too. So that's it for me. Are there any final questions or comments as to some of the material that we covered today? Or in general on type classes, just anything on type classes? Because I know I've been beating this with a stick like the lat and been reiterating this over and over again. But this is actually really, really fundamental to the Haskell type system. Functors are built on top of this. Applicatives are built on top of this. Monoids are built on top of this. So if you don't understand how type classes or the type dispatch system kind of works, that is you're working at a disadvantage. You just need to have some sort of fundamental understanding in order for you to start working through some of the higher level concepts. Okay, guys, I appreciate you guys joining us this Sunday. I'll see you guys next week. And stay tuned for announcements. For those of you who are not on our Atlanta Functional Programming Meetup page, please consider joining. That's when you get announcements of episodes, other events as part of our running lecture series, as well as meetings, of course, for other languages, such as our Common Lisp Study group that is held every Saturday from 1:30 to 3 Eastern Time. And with that, I leave you guys, and I wish you all a good day. See you.